All right, Euler's method here. This is the first time I'm doing a video like this, so you guys have to tell me if this is working well or not working well or whatever here. Okay, but 10.3, that was about Euler's method. All right. Now, Euler's method is a numeric way of estimating a curve. All right, so we don't have to solve it analytically. We will, but you don't have to. Okay, this is when that doesn't need it. And this is used to estimate a function. Okay, you may not be able to solve it. Okay, so the general idea here is you're going to have a dy by dx. Remember, that's a slope. Okay, remember that's a slope, and that is equal to some function g of x, y. This is the standard form. Yes, my cat has a lot to add here. This is the standard form of the differential equation we want to solve. Okay, dy by dx. All right. So where this comes from is saying we're going to approximate this. We're going to say instead of dy dx, we're going to say delta y delta x. Okay, and we're still going to say that that's equal to gxy. Again, this is the value of the slope because that's what dy by dx means. It's the slope. Okay, and then what we're going to do is we're just going to multiply both sides by that delta x. So we're going to have dy dx, oops, we're multiplying, that's equal to gxy delta x. All right, we have delta x there. So now that we have the delta, right, delta means the same thing in math as it means in science, is that we're going to go ahead and say it's one or the other. All right, so we're going to have, this is y new minus y old. Okay, and that is equal to g, and since we're evaluating the function, we're going to go ahead and put a point in here. So we're going to say x old comma y old. Okay, we don't have what the new value is yet, so we are stuck using the other values that we do know. Okay, and then this delta x, well, textbooks since the 1980s don't like rating delta x, they like rating h, so that's what that is, it's an h. Okay, they have to tell you what h is in the problem description for you to do the problem. So if they don't tell you what h is, it's like they didn't tell you what g of xy is. You're not doing anything unless you have some information. Okay, so they'll typically tell you that h is equal to 0.01, 0.11, something typically considered to be kind of small, 0.0001, something like that. Okay, so graphically, what's going on here, the idea, all right, is that we're given some initial value, x0, y0, that's our old points, all right? And then what we're going to do is we're going to take our old point, we're going to plug them in. Remember, this is the slope, okay? This gxy, that is the slope. So they're going to evaluate some kind of a slope here, and we're going to take it by one step. Okay, so we're going to go with one step. I'll make it out the step, and that'll be our slope. All right. Now we have our new point, but now we want a new point. So this is now the old point, and then we're going to get another value. So we're going to evaluate the slope here and take a step. Okay. Once we're here, we're going to evaluate g of xy, which again that's the slope. Right, and it might do something like this, and then we're going to jump up a step, okay, and it might do something else, and then we're just going to keep going with this until we've approximated our function. All right, so the idea here is that you can use this method if you can't solve a differential equation, and we lie to you in differential equations classes and in calculus by giving you ones that you can solve, when the reality is you can't solve, the ones in real life are ones that you can't solve. So you're always doing something like this. Okay, so that gives you some options. Conceptually, what you're trying to do with this, if you've ever had the pleasure of walking a dog without a leash, what the dog does is it checks where its human is, right? And then it bounds forward. Okay, if you have a fairly well-behaved dog, it'll bound forward wherever steps it does. But then eventually it'll look back at you. It'll say, what direction is my human facing? And then it'll bound forward in that direction. And then once it gets comfortable bounding forward, it'll look back at its human and say, well, what direction is it facing? And then it'll go forward in that direction. And this process kind of continues as you're walking your dog. And your dog is going all over the place. But the idea is that it checks where you are and then goes in that direction. Okay, it checks which direction you're facing and it goes in that direction. It checks which direction you're facing and it takes a step in that direction until you've completed your walk. Okay, so that's the idea. What this problem is going to look like, all right, you're going to get a dy by dx is equal to, say, something like 3 over x. Just by coincidence, I'm picking the problem that we're going to do next, okay? And then it'll tell you something like dx or h is equal to 0.1. Okay, that's a very typical for our book, is it's 0.1. This is not written in stone. It doesn't have to be 0.1. Your book just likes 0.1. Okay, and then you can go ahead and solve this differential equation numerically rather than analytically. We're going to solve it both ways, but it's only a separable DE. It's not going to be a terrible thing to do. But we'll solve them both ways, and I'll take you through the process of doing this by hand. Okay, so thank you. Please give me feedback about what's going on here. I hope everybody is doing well with the forced isolation, and we can do our classes that way. All right, thank you.